Good afternoon. The second lecture in our COVID-19 series will be about Colombia and the Boring Billion. I hope everyone's doing well. And in order to kind of go through what this supposed Boring Billion is, it's believed, or at least it was believed, that during the time interval from about 1.8 to 0.8 billion years ago, it appears that the Earth went into some sort of, we'll call it a stall or a stasis with regard to geobiological processes. And the reason for this idea is that when geologists started looking at trace elements, stable isotopes in particular, of oxygen, of carbon, of sulfur, it seemed that the levels, which typically vary with biological process, kind of just went into a stasis. And that includes oxygen here. We had this great oxygenation event that we talked about before, where oxygen levels rose. And then you can see for about 1 billion years in here, especially from about 1.8 to 0.8 billion years, not much change in the oxygen levels. So that led a lot of people to believe that, well, there really wasn't much going on in this Boring Billion. People looked for evidence of life, of some transition in life, and it was really hard to find. And so this has been nicknamed the Boring Billion. Since that time, a number of people have questioned whether or not this truly is some strange interval of time where nothing really happened exciting on Earth. And in looking at stable isotopes, that certainly seems to be the case. There's not a lot of variation in stable isotopes over this time. But geologists started looking at other types of tracers, such as trace elements, and these are just elements that aren't common in most rocks, but they do vary according to environment, and tried to tie these to sort of evolutionary events. And in this graph, you can see that these trace elements over that billion years, from about 1.8 to about 800 million years in this time, you can see there are quite a bit of variation within those trace elements. And furthermore, upon detailed investigation, it appears that a number of biological innovations took place during this so-called Boring Billion, including endosymbiosis at about at least older than 1650, the first eukaryotic cells and cell organelles, multicellularity, perhaps as early as 1600 million years. That includes then sexual reproduction of about 1600 million years. And then diversification and radiation of the eukaryotes, so from mainly prokaryotic life to eukaryotic life, and even the crown group eukaryotes. And crown group are kind of where where all eukaryotes came from. So it doesn't appear, if you look at this carefully, although the stable isotopes are telling one story, if you look in details in other things like trace elements, if you look at some geobiological indicators other than stable isotopes, it's anything but a Boring Billion. Turns out that that's true also when we look at tectonic events. And in particular, the oldest supercontinent that has so far has some reasonable data to support its existence, and that is called the Columbia supercontinent. Some people call it NUNA, N-U-N-A, but for most of us, we call this the Columbia supercontinent. And this is the oldest large amalgam of continental blocks that developed between 1.8 and 1.5 billion years ago, right in that Boring Billion year interval. Not only that, but it appears that many smaller little Archean age nuclei, so think of these Archean age nuclei as sort of the first continental blocks, those granite greenstones, tonalite, trondhjemite gneiss belts. And it appears that those coalesced into larger masses between about 2.0 and 1.7 billion years. So as this supercontinent was assembling, not only was the supercontinent assembling, but it also appears that continents themselves, larger continents, were also forming. I'll give you a couple examples. Here's a map of North America. A lot of different colors in here. What's important is to look at these these dark red or pink colors, the Wyoming craton, the Superior craton, and the Slave Ray Hearn province. These are Archean nuclei that were welded together by about 1.7 billion years. So it appears that tectonically, again, anything but boring, as North America was being formed, and probably much of North America was assembled during this BoringBillion. You can see even here at the tail end of that BoringBillion, this Grenville belt, and we'll talk about that when we get to Rodinia. But this is the second formation of a supercontinent at younger times. So from a tectonic standpoint, at least, it's anything but boring. We can look to India. This is based on the work of my students and myself, and you can look at the little pieces of India. This map is not showing up. That's okay. India is made up of about 5 pieces: Dharwar, Bastar, Shingbum, Aravalli, and Bundelkhand. And if we look at this, the assembly of these pieces, it looks like at about 1.8 billion years ago, right at the start of that BoringBillion, we have 3 big pieces of India coming together. These are the southern India blocks. And then during about 1.1 to 1.0, again during this BoringBillion, we have these northern India blocks that become attached to the southern India blocks. So again, tectonically, anything but boring. You can go to Baltica or Northern Europe. You can go to Siberia. You can go to Africa. And you'll see the same sequence of events, these smaller cratonic nuclei, these ancient blocks coming together during that BoringBillion interval. If we start thinking about supercontinents and how supercontinents form and how supercontinents break apart, all we have to do is think about the fact that if plate tectonics was operational, and I'm going to argue from the standpoint that plate tectonics began sometime in the Archean, and that the continents were moving and that oceans were opening and closing, then it should be no surprise that sometimes continents might be closer connected and sometimes further apart. And we kind of do this, imagine a random walk of continents across the globe, kind of illustrates this nicely. So think of each of these lines here, each of these lines showing some continent moving. And if you look, you can find little intervals of time where it appears that many of these continents seem to meet up. So this would be the formation of supercontinents. Kind of a simple illustration, but it's a good way to think about how continents move on Earth, how they get together, and how they might break apart. If we look at some of the supercontinents that have occurred through time, of course, we'll talk more about Pangea when we get to the Paleozoic, but the supercontinent that's most familiar to everyone is the Pangea supercontinent that lasted from about 300 to 180 million years. It was made up of 2 halves, the Gondwana half, which are the southern continents, and then the Eurasia or Laurasian continents, which include the northern continents of Laurentia, Baltica, which is northern Europe, and Siberia. This was first, of course, envisioned by Wegener in the early 1900s, and it is the first documented supercontinent. It's not the oldest supercontinent, but it's the first supercontinent that geologists have some confidence that we understand what happened, how it came together, how it formed, and how it broke apart. If we go a little bit earlier than that, I hope that's not the COVID-19, sorry. If we look a little earlier than that, this is about the time that I was going to school, getting my PhD, people began to look back in time. And in 1984, a little bit before that, when I was still an undergrad, Gerard Bond and others proposed the existence of a Neoproterozoic age supercontinent based on the ubiquitous presence of passive margin sequences around the globe. And they suggested the supercontinent broke apart right at the Precambrian-Cambrian boundary, somewhere around 541 million years ago. And this is what they imagined it looked like, that North America here was attached to South America, Baltica up here. So Gondwana was fully formed, and it was attached to North America. Well, what is a passive margin and what's an active margin? Well, these two types of margins, an active margin is where you have oceanic crust subducting beneath continental crust, and it's called an active margin because along this margin you have earthquakes, you have volcanoes, you have metamorphism going on. So it's a very active region of the Earth's surface, and it's where two plates are colliding with one another. On the other hand, if you go to a ocean continent margin where there's nothing going on, so in this case, I think this is the middle of the Atlantic Ocean here, you do have seafloor spreading, so you have some activity in the middle of the seafloor, but the continent and the attached ocean is just passively riding along. There's no destruction here, there's no addition, there's no construction along the continent-ocean boundary, so these are called passive margins, and these develop when continents break apart, right? You have seafloor spreading, that means the ocean is getting bigger. And the fact that they found these passive margins on many, many continents, continental blocks, right around the Precambrian-Cambrian boundary suggested to them that a large supercontinent broke apart. In the late 1990s, two geobiologists, Mark McMenamin and his wife, proposed that there was a supercontinent, and they called that supercontinent Rodinia. Rodinia comes from the Russian prefix rodit, and that means to beget, and the idea that this was the oldest supercontinent and that this was the forerunner of all supercontinents. So if you think of it in a biblical sense, so-and-so begat so-and-so who begat so-and-so. The idea here is that Rodinia was the mother of all supercontinents, and it gave birth to all subsequent supercontinents. There was some data supporting this, including a number of orogenic belts, mountain building belts, that were dated between 1.1 and 0.9 billion years, again during this so-called BoringBillion years. We apparently have collisional belts, continents colliding with one another during this interval of time, and this is something that's seen globally. You can find these orogenic belts of this age just about every continent that you go on. You can find younger Neoproterozoic rift basins and passive margin sequences around the globe. This is what Gerard Bond and his colleagues noted. And then you can look at geologic, geochronologic, and paleomagnetic evidence that are supportive of this, but often highly divergent on an exact makeup of that supercontinent. So we have evidence in these orogenic belts of continents colliding. We have evidence in these passive margin sequences and rift basins of the supercontinent breaking apart in the Neoproterozoic, and a number of paleomagnetic and other data supporting this Rodinia supercontinent. Well, what did it look like? Again, it comes from the Russian prefix rodit, means to bring forth. It is the supposedly oldest supercontinent with strong evidence, and I think that now we can say that Colombia is probably the oldest supercontinent with strong evidence. It lasted from about 1.1 billion years ago to 750 million years, making it perhaps the longest lasting supercontinent. We're not sure when Colombia formed. Colombia lasted maybe 300 million years. This lasted about 350, so they're pretty close. And the makeup of Rodinia, just for reference here, here's North America. Florida is not attached yet to North America. We'll talk about when Florida became attached. But Amazonia and Rio Plata, these are blocks that now make up parts of South America. If you were to walk off the coast of California, you could walk into Australia and Antarctica. And over here is Northern Europe, North China, and Siberia. So this is one iteration of what people think Rodinia looked like. This is in a bit of a state of flux because as we gather more data, we have different ideas of how Rodinia might look. The Columbia supercontinent is shown here. This was first proposed in 2002. The evidence for this supercontinent, for the makeup of this supercontinent, is slim. And by slim, I simply mean that we don't know exactly where these pieces were. And if you look carefully at this supercontinent, you'll see that here's Eastern Laurentia, and it was attached to South America. That's really not much different than in Rodinia, and furthermore, if you look at the west coast of present-day west coast of North America, you would walk into the Mawson continent, which is Antarctica, or perhaps Australia and Siberia. So Colombia and Rodinia, at least at present, look very, very similar to one another, which kind of begs the question: is why are they so similar? What was going on during this interval of time that allowed one supercontinent to form, to break apart at 1.5 billion years ago, and then come back together in almost this exact same configuration around 400 million years later? We're not sure. I would argue that probably our ideas of the makeup and the positioning of these continents within Colombia may be wrong. As more data come along, we can consider these models and develop these models further. What we do know is that there's plenty of evidence for orogenic belts within Colombia. So we see these sort of they start actually at about 2 billion years to about 1.7. We see lots of orogenic belts. That means mountain building. That means continent collision. And then we see a lot of basins forming around 1.5. We see these rift basins, these passive margin sequences developing. So the same sort of evidence that was used to argue for Rodinia is also used to argue for Colombia. If we look a little bit further, we know that actually the continents on Earth are not in a true random walk. A true random walk is often referred to as a drunken walk, where each step is, it's unknown which direction a continent will move in each step. That's what's called a drunken walk, or a standard random walk model. The Earth doesn't operate quite that way. The Earth is not a perfect sphere. If we look at it in detail, the hotter regions are elevated and the colder regions are depressed. And supercontinents must form and also break up based on how these thermal forces drive the continents together or apart. So the pieces may reassemble in the cold, low spots, turning them later into hot regions of the mantle. I'll show this in a picture on the next slide. So if we kind of look at development of the supercontinent, so we have a supercontinent here sitting on top of the mantle. It's kind of a lid. So this continent is a very large piece of continental crust sitting on top of the mantle and probably surrounded by subduction zones here. And of course, the Earth is trying to get rid of heat. So what happens is it kind of deforms that sphere. So in an idealized model, you can see that supercontinent forms sort of a bump on the Earth, raising that supercontinent lid up. And as time goes on, as more and more heat builds up beneath that supercontinent lid, that bulge gets larger. And then eventually, both because of the buildup of heat beneath that supercontinent and also because of just gravitational potential energy wanting to pull that, you're up high now, so that continent's going to want to move off, you begin to break up the supercontinent along these zones of weakness, and the supercontinent begins to break up into smaller pieces, and those smaller pieces then migrate away from that bump and move towards lower areas, and they might reassemble back over here. So it's kind of a sequence of continents moving away from hotter spots and moving towards cold spots that causes supercontinents to form and break apart. All right, so what happens, just for fun, if we think about, well, what's going to happen in the future? And about 250 million years in the future, if things go as they are, we will have the next supercontinent, and it will be called Amasia. And the reason it's called Amasia is because the Americas will be against Asia. So America is the M in Amasia, and of course Asia is the Asia. So it will look something like this, with Africa then positioned against Europe, Antarctica moving up against South America, and Australia kind of sandwiched between South America and Asia. We don't really know this is going to happen. This is just based on sort of modeling, very simple modeling, saying, okay, if everything moves the same way it is moving today, this is how we'll end up in the future. All right, so if we start thinking about some of these important events in tectonic history, and we get outside of that boring billion, we still don't know a lot about what went on. We know about the tectonic events that went on, the formation and breakup of Columbia, and then the formation and really the breakup of Rodinia also occurred during that boring billion. But after that, when we start moving from into the Neoproterozoics, that last little interval in the Proterozoic, we start seeing some really strange things going on. And the first thing that we see is we see this breakup of Rodinia, and then we see some really, really strange stuff in the Earth's climate record. And this strange event, actually not one, but at least two of these strange events are called Snowball Earth. What is the Snowball Earth? Well, it's a period of time when the entire Earth may have been glaciated from the pole to the equator. So if you were to look at the Earth from space, instead of looking like a blue marble, it would look like a white or vanilla ice cream cone. It would be completely covered in snow and ice. And the question is, what exactly happened to cause the Earth to go into this snowball? And it's an important consideration because what we know about the temperature regulation on other planets suggests that once you ice over a planet, it's very, very hard to thaw it out. So what a number of people have been studying is, okay, how do you trigger a Snowball Earth episode, and then how do you get out of it? So how does the Earth go into a snowball? How does it come out of a snowball? And in the case of these Snowball Earth episodes, it appears that it happened at least twice. So we have evidence for at least two snowball episodes. Some people have suggested maybe 3 or 4. And that's highly unusual for any planet to be able to go into and out of these snowball episodes. So how do we know? Well, we look for these evidence of glacial rocks all around the globe, and just about on any continent you go to. One exception that I know of is in India. We don't have evidence for this, but it may just be we don't have rocks of that age. But we look for these big boulders that are dropped by glaciers. This is the Muldtillite in Norway. It's a younger version of me. And you can see these big boulders that are these, think of the ice picking these up and then dropping these blocks out as some of the ice melts, and that's what a tillite is. This is very common even in modern glacial deposits. If we look at it more closely, you can see some of the smaller, here's some of the smaller pebbles within the Muldtillite. That's an old-fashioned camera lens cap for scale, but you get kind of this dirty, grimy rock with a lot of these drop stones into it. And everywhere you look, you can find these tillites, these evidence of glaciation. So what exactly triggered this glacial episode? Well, we think about greenhouse gases, and one of the things that we have to do in order to trigger a snowball Earth is to draw down the greenhouse gas CO2. So we have to remove all that CO2 from the atmosphere. And our argument, this is my colleagues and I from France, we made this argument that the drawdown may have been caused by the tropical weathering of basaltic rock. And I'll explain this in a little more detail shortly. We also know that during the Snowball Earth episode, the sun was about 5 to 6% less luminous. What does that mean? As stars evolve, they get brighter and they give off a little bit more heat. So if we go back to the Snowball episodes, the sun was 5 to 6% less luminous. That doesn't necessarily mean a lot. That's a small percentage, but it may have been just enough that, coupled with the drawdown of greenhouse gas, it may have been just enough to trigger these snowballs. Furthermore, there wasn't a lot of biomass around to produce extra CO2. There just wasn't a lot of life. plants, there weren't animals, there was not a real active biological cycle that could produce extra CO2 or withdraw CO2 from the atmosphere to create some sort of balance. So you have to think about all of these things when you think about snowball Earth trigger, and then you have to think, well, how do you get the Earth out of the snowball? So here's kind of the sequence of events that's been envisioned for how a snowball Earth develops and sort of what the temperature looks like. And at the beginning of the snowball, you have CO2 levels about, say, roughly about the same as today. So 1 is about the same as today. Anything greater than 1 means more CO2. Anything less than 1 means a lot less CO2. And so you get some initial cooling, and ice starts to form at the poles like it does today. And that ice, of course, reflects incoming solar radiation out into space. If you ever go skiing, you know you wear sunscreen on the ski slope because the sun is reflected off the snow, and it can be very, very bright enough to cause sunburn. So all this is telling you, these albedos here are just telling you that about 30% of incoming solar radiation is bounced back out into space. That means it's not available to warm the Earth. The temperature on the Earth, the average temperature on the Earth, is just above 0 degrees centigrade. So we start to form ice at the poles. As we start to pull the CO2 out of the atmosphere even more, we get down to about 1/10 or less of the current level of CO2. And now what happens is the ice gets to about 30 degrees north and south of the equator. And as soon as it gets to 30 degrees north or south of the equator, it goes into a runaway snowball event. The albedo kicks up to about 60%. So instead of only 30% of the incoming solar radiation bouncing back out into space, you have 60% of the incoming solar radiation bouncing back into space. And the overall temperature drops to minus 50 degrees centigrade. And then the third stage is where the entire Earth is glaciated. The albedo is about 70%. And now what happens, if you look in the ocean, you've now covered the ocean with ice. So all the volcanic activity, that volcanic activity in the ocean, that it still continues. It's still releasing CO2. Volcanoes are a tremendous source of CO2 in the atmosphere, especially in the Precambrian. As CO2 is being released into the ocean, but it's meeting a cap of ice. So the CO2 is building up underneath the ice cap. I call these Coca-Cola, I guess, because we're Florida, we have to call it a Pepsi-Cola ocean. But these are carbon dioxide rich waters, but they're buried beneath the ice. Well, at some point, you do have enough volcanic activity and you have enough other activity, you're going to crack the ice. And the minute you crack the ice, you're going to release all that CO2 up into the atmosphere. And instead of getting a runaway ice house, you're going to get a runaway greenhouse. And so here, the Earth heats up because of all that excess CO2, and temperatures reach about 50 degrees centigrade. All right. So that's the sequence of events that's envisioned for how you might trigger this snowball Earth. And in the rock record, what we would expect to see is we would expect to find these tillites, which we do find. But the funny thing is that sitting on top of those tillites, conformably overlying those tillites, are these really pink dolomites or limestones sitting right on contact, which means that you went from a very, very cold climate to a very, very hot climate with practically no time in between the two. And that association of these tillites with these pink dolomites is what led people to conclude that we went from a rapid icehouse conditions to rapid greenhouse conditions. So our group was tasked with sort of modeling this. What sort of tectonic environment must you have in order to trigger a snowball Earth? And so we looked at the paleogeography. I did the paleogeography. I had people from France who were doing the climate modeling and weathering modeling. And we put this into the model, and we had the breakup of the supercontinent. And if you look at it, most of Rodinia was located around the equator. There were a few continents down here at a little bit higher latitudes, but most everything was either, somewhere close to the equator, say within 50 degrees of the equator. Oceans covered both polar regions. There weren't many continents sitting up at the poles. The carbon dioxide decreases in the atmosphere, triggering the initial cooling and the formation of ice sheets at the poles, and then continued cooling causes this is called the Budko effect, which is this runaway ice house. And so you end up with this ice-covered planet Earth. Now, what's interesting about this is that it seems that you have to have a supercontinent that's breaking apart. You can't have an assembled supercontinent, and you have to have volcanism. So our argument was that if you have a lot of volcanism, which kind of counterintuitive, if you think about volcanism, it should be pumping CO2 up into the atmosphere. Everything should be getting warmer, right? Because CO2 is a greenhouse gas. So this mafic volcanism that's taking place between 800 and 720 million years as Rodinia broke apart is pumping incredible amounts of CO2 into the atmosphere, which is a greenhouse gas, an anti-snowball. But it turns out that as you break apart a supercontinent, you also increase the hydrologic cycle. What does that mean? It rains more. When you have a big continent, the interiors tend to be dry. You don't weather things. When you break it apart, the interiors can then get wet because the evaporated water from the ocean can reach the interiors and rain out. What does that do? Well, that starts to weather the continental rock. And that is important because it turns out that when you weather continental rock, you create clays, and clays lock up carbon dioxide. Okay, that's a lot to think about, I know. So let me just sort of summarize. What we had during this time interval is we have a supercontinent that's breaking apart, and it's breaking apart because of all this heat being released and all these volcanoes erupting, pumping CO2 into the atmosphere. Intuitively, that would make you think, well, this is going to be a period of Earth history where everything was warm. But it's not, it's cold. So our question was, well, how do you get all this CO2 in the atmosphere? You have to pull it out. You have to get it out of the atmosphere. So that's where these climate modelers came into the story, and they started looking at what happens when you have a supercontinent, what happens when you have a continent that's breaking apart, and what happens when you have a supercontinent that's breaking apart with a lot of volcanism. So here's kind of our model end runs. Here's the assembled supercontinent with low weathering rates. Remember, interiors of these supercontinents are going to be very dry, not an active hydrologic cycle. And then as you disperse this supercontinent, you're going to see higher weathering rates. And this shows up quite nicely in terms of runoff and in terms of rainfall and so forth. So when you have this situation, you have a lot more rainfall, you have a lot more runoff, you have a lot more silicate weathering. Then they plugged this into a couple of models. And the first model that they plugged it into is they just said, okay, let's forget about volcanism. Let's just sort of as a base for our models. Let's forget about volcanism, and let's have a model here where we have a supercontinent, and then we'll have a model here where that supercontinent breaks apart. We're being a little bit, funny here because we know when a supercontinent breaks apart, there is volcanism associated with it. We wanted to just see if just breaking apart a supercontinent would be able to lead to a snowballer. So here you can see CO2 with a supercontinent. CO2 levels are quite high. They do drop down with a dispersed continent. So there is some silicate weathering with a dispersed continent. But you can see what we have to do. We have to reach this level in order to get to a snowballer. You can see that CO2 doesn't reach that levels. So the next set of models we ran was a supercontinent with no volcanism. That's the same as up here. And then we added a supercontinent with trap volcanism. Trap is just basaltic volcanism. And then a dispersed continent with trap volcanism. So we can see here with the supercontinent, we still have high CO2. Even if we have volcanism on that supercontinent, within that supercontinent with high CO2, we end up with high CO2. We really don't pull much CO2 out of the atmosphere. But look what happens when we start to have this continent disperse. We have trapped volcanism associated with it. Then we can pull out enough CO2 to trigger the snowball Earth. So this is one explanation for how you can end up with a snowball Earth. And the backdrop of this, it's important to remember that the backdrop of this, and the reason that these models can be so simple, is because from a biological perspective, there wasn't much going on. There weren't animals on land, there were not forests on land. Most of the organisms in the ocean were blue-green algae, maybe small eukaryotes. There just wasn't an abundance of life, and that abundance of life helps regulate CO2 quite naturally in the modern Earth that didn't exist at this time. If we look at the carbon isotopic record for these time periods, you can see it's a little bit noisy here, but basically during these glaciations, the CO2, which is recorded in Del C13, the CO2 drops off during the Sturgeon, and then it rises back up and then drops back off during the Maranoa. And these are the two big glaciations. There's been another one suggested here during the Bitter Springs. You can see CO2 drops. Perhaps there's a glaciation there. But you can see this drawdown of CO2, this drastic drawdown of CO2 here for these two big glaciations in the Neoproterozoic. And these are the two episodes that people call snowball Earth glaciations. The Maranoan snowball, which is the younger one, there's two, the Sturgeon is the older one, the Maranoan is the younger one, it ended at 635. Well, why is that important? Well, 635 marks the onset of the Ediacaran interval. So the Ediacaran period in geologic time is actually denoted by the end of the snowball Earth. So that's why the Ediacaran starts at 635. There is evidence for younger glaciations, maybe at 580 and 550 million years ago, but they were not snowball. There's no evidence at that time that the entire Earth was glaciated. And it turns out that following this snowball Earth, there's these strange multicellular organisms begin to pop up in the fossil record shortly after the Maranoan snowball event. So one argument is that this snowball to ultra greenhouse back to snowball, if you think about whatever organisms were around at that time, when the Earth iced over completely, that is a tremendous stress on whatever life is around, right? You're freezing that. You're all the life that's around has to adapt to that. Probably what happened is that there were major extinctions during that time. We just don't have a good record of it. But it probably stressed the biological environment enough that it created a biological bottleneck. And then when the temperatures rose and the Earth melted, then you would have kind of a flush. So the idea, these are called bottleneck and flush episodes. So you have a bottleneck where life is stressed, and whatever life makes it through comes back out into a very nice environment, and it flourishes again, so you get a flush. And then you get a second episode of bottleneck and flush. And so some have hypothesized that it was these snowball Earth events that led to the radiation of the Ediacaran organisms, of these really strange multicellular organisms that began to pop up in the fossil record shortly after the Maranoan snowball event. That's a little dicey, I have to tell you, because we really don't see a rich record of these Ediacaran organisms until after about 580 million years ago. That's when we really start to see these organisms proliferate in the fossil record. If you think about that, that's 55 million years after the end of the snowball. That's a long time for biological life to respond to rapid climate change. Generally, with the bottleneck and flush episode, if you think about probably one of the more recent bottleneck and flush episodes was when the asteroid hit the Earth at the Cretaceous Paleogene boundary. that bottleneck and flush episode, basically the bottleneck killed out all the dinosaurs, the flush through was the mammals, and the mammals took over the earth fairly quickly. We didn't have to wait 55 million years for mammals to take over the earth. In fact, if you think about it, if it took 55 million years and the dinosaurs died out at 66, that means that we wouldn't have seen anything in the fossil record till about 11 million years ago, which is completely not what we see. So there's some debate as to whether or not these snowballers were an effective biological radiation mechanism or trigger. All right, so I'll stop there.